In this lecture, we're going to discuss some theories about what in fact is happening during classical conditioning. What type of associations are made? So let's first think about what kind of associations are made between the CS and the US. Does the CS predict the onset of the US? So a bell rings, the animal doesn't think bell is food, they think the bell tells them the food is coming. It's a predictor. That's a possibility, and it's probably true to some extent. The other idea is what I just said, is the CS becomes, in a way, like the US. It becomes a substitute. This is called the stimulus substitution theory of classical conditioning. So a key light comes on and food drops in auto shaping. The key light does predict the onset of food, but the animal still pecks the key. So it may be that the key light becomes, in a way, a substitute for food after that association. So let's think about that. One possibility is that the key light becomes a substitute for food, and in this case, one might expect the behavior to be a little bit different if the key light is associated with water versus the key light associated with food. One way to investigate this is to do an auto-shaping experiment, but have the reinforcer either be food or water, and look to see what the animal does with its beak. Because an animal, like a bird, will drink water with its beak shut, but will open its mouth, open its beak, when there's food. So if there's a substitution, then if the key light is associated with water, we would expect the animal to keep its beak shut. If it's associated with food, we would expect it to keep its mouth open. So here's a video that demonstrates just that. This is an auto-shaping experiment with a pigeon with grain versus water. Okay, so its beak is open. This is because the key light is associated with grain or food. See its beak opening. That gives us an idea that that's a substitution. Now this is pecking with water. You can see the beak is shut. The animal naturally drinks water with its beak shut, so the conditioned response is pecking with the beak shut. The unconditioned response to food is to open the beak, and so the conditioned response is an open beak pecking. So that video gives some indication that the key light becomes a substitute for the unconditioned stimulus. If the unconditioned stimulus is water, the conditioned response is pecking the key light with the beak shut. If the unconditioned stimulus is pellets of food, the conditioned response is pecking the key light with the beak open. Okay, another thing that can happen is that the conditioned response is not the same as the unconditioned response. This can happen sometimes. It's really important when we talk about such things as drug tolerance. This is known as a condition compensatory response. To compensate. In other words, the conditioned response can be the opposite of the unconditioned response. Let's give some examples. So, if you ring a bell and give an animal insulin, insulin causes blood glucose to go down. Just inject insulin, blood glucose goes down. Insulin helps bind up glucose. However, if you associate a stimulus with insulin, the conditioned stimulus does just the opposite. It compensates. It produces a compensatory response in that it elevates glucose levels. In other words, if the CS tells the body insulin's coming, then the body should go, oh, I need to up my glucose because in just a minute, my glucose is going to go down. It compensates. Same with adrenaline. This has been done with animals. Show a light, give the animal a little adrenaline. Light adrenaline, light adrenaline, light adrenaline. association. The natural response, the unconditioned response to adrenaline, is for the heart rate to elevate. It increases your heart rate. But the conditioned stimulus, if the animal has that association, the conditioned stimulus produces a compensatory response. In other words, the CS causes a heart rate to go down. The conditioned response is heart rate goes down. The CS causes a compensatory response. Now, this is really important in issues with drug tolerance. So what we know, just statistically speaking, that people who are addicted to drugs, such as opioids, like heroin, fentanyl, oxycodone, they will, if they overdose, they tend to overdose in unfamiliar environments. This is because of a conditioned compensatory response, or what's known as psychological tolerance. Okay, let's give an example of what I mean here. Suppose a person starts taking an opioid, a drug like heroin or fentanyl or oxycodone. They will begin by taking a low dose. They don't want to overdose, they take a low dose. They typically take the drug in the same location, at home, in a comfortable place. And the stimuli in that location become a conditioned stimulus or stimuli. The environment, they're taking it home, the smell of their couch, the sight of paintings on the wall, whatever, becomes stimuli that tells the body an opioid's coming. Every time I take out the needle, every time I begin to prepare the drug, those are stimuli. Tells the brain, this drug is coming. And what happens is the body prepares for it. The brain is seeing this as, I don't want heroin and fentanyl and oxycodone in my body. I want to break it up. I don't want to let it get to my brain. So what happens when a drug is taken like this, the liver releases chemicals, enzyme, what are known as metabolites, that break up the opioid and keep it from getting to the brain. The conditioned stimulus of being in this environment where they normally take the drug is telling the brain an opioid is about to be injected into your body. So the conditioned response before the drug is even taken is for the liver to start producing these metabolites. And so when the drug finally gets into the body, the metabolites are waiting and break them up. And so not as much of the drug gets to the brain. If the brain knows the drug is coming, it prepares, it compensates. That's all Pavlovian learning. And so less gets to the brain, that's known as a tolerance. Tolerance simply means a person has to take more drug for the same effect. Well, since not as much of the drug is getting to the brain, they have to take more. They increase their dose to get the same effect. They used to take a small dose, but now they take a higher and higher dose. There are other forms of tolerance that happen at the cellular level, but this is psychological tolerance. Sometimes it's called situational tolerance. In other words, the body becomes tolerant to the drug at that specific location and time because the conditioned stimuli say, okay, this drug is coming. But now they're upping their dose. They then take the high dose in an unfamiliar environment. It can happen. Let's say, as just an example, some friend who also takes these drugs invites them over to their house. They've never been to their house. Come over to my house and we'll take these drugs together. And when he gets there, well, how much drug do you take? Well, I used to take this very small amount, but now I take a lot more because I've become tolerant. But in this new environment, the conditioned stimuli are not there. This is not a conscious thing. The brain isn't going, you're consciously saying, oh, I'm going to make the liver release these metabolites. No, it's conditioned stimuli that causes it. But now we're in a new environment. The couch isn't there. The smell isn't there. The things on the wall aren't there. These are new. So the brain does not know the drug is coming because not all of the stimuli are there. There may be some, but not all of them. Not all the stimuli, so you're not going to get the same level of conditioned response because they're different stimuli. So the liver is not getting information from the brain that an opioid is coming. So they're not sitting there in the blood with these metabolites waiting for this drug because it doesn't know it's coming because they're in a different environment. But this person is still taking a very high dose, and more of that drug gets to the brain, causing an overdose. They still take the higher dose, but we don't see the situational tolerance, the psychological tolerance, conditioned compensatory response. These all mean the same thing. Now, I'm just using these numbers as examples. I don't know how much people take, but this is just an example. So this is the number of times they take the drug. At the first, they take the drug. There's no compensatory response, and all of the drug that is taken makes it to the brain. I have that in orange. This is just an example. But the more they take it in the same environment, the more the person increases their dose, but the same amount gets to the brain. Why? Because stimuli are there to tell them, oh, you're about to take an opioid, let me release liver metabolites to break it up so it doesn't get to the brain. These are conditioned responses. So even though they take more, the same amount is getting there. This is conditioned compensatory response. But let's say, again, this is an example, this right here is some level of overdose. If it gets to the brain, if it is not broken up in the blood. I'm just saying, let's say this line, this amount is an overdose. They're taking more and more. Look at right here. The 9th time they take it, they're taking way more of the drug than they should. They're taking way more. It's going to cause an overdose. But because we have this compensatory response, this Pavlovian response to break up that drug, because the brain knows it's coming, this whole dose doesn't get to the brain. This much does. So they take more and more and more. And let's say here, they're invited over to their friend's house. And the stimuli are different. You're still going to get a compensatory response, but not to the same degree because the conditioned stimuli are not there. And more gets to the brain, and we get an overdose. Classical conditioning tells us a lot about drug tolerance, but it also tells us why we have a statistic that people tend to overdose in unfamiliar environments. Okay, on to a different topic. If you remember this slide from a previous lecture, we talked about excitatory associations being created. Now, we start with this assumption that a stimulus, a light, creates a pathway or an association or a connection with another area of the brain that is somehow involved with a stimulus. We get a stimulus-stimulus association. Sometimes we just call that SS association. But I mentioned that as conditioning continues, we can get just a stimulus to response. The area of the brain that's responsible for responding is active when the green light is on, so they connect. This is known as a CSCR connection, or just SR. SS, SR. So what's happening in the brain? We can run some experiments that give us some insights into this. So there's an association made, but is that association SS or SR during classical conditioning? That's the question that people have tried to figure out, and I'll give you the answer. Both. But we have some evidence, some experimental evidence that one is happening, and we have some experimental evidence that another is happening. So let's look at that experimental evidence. This is support for the SS idea of association. There's a few experiments like this, but let's look at one. This is called sensory preconditioning. And you'll need to know the methods for doing a sensory preconditioning experiment and what the results tell us. the first thing you do is you pair two stimuli together. There is no response. A red light comes on, a green light comes on. The red light and the green light are in temporal contiguity. We do this many trials. One can assume that the areas that in the brain that represent these stimuli are become associated. But the animal's not salivating, he's not pecking keys, not doing anything. There is no opportunity for a stimulus-response connection because there is no response. The animal's just looking at these things. They're just staring at them. Red light, green light. Red light, green light. And the question is, did the animal in fact make a connection that when the red light comes on, the green is going to follow? That's what we need to test. So we take the second stimulus and we do condition it to a response. Let's say we're using the eye blink conditioning. Green light comes on, animal gets puffed in the eye. Green light comes on, animal gets puffed in the eye. Green light comes on, animal gets puffed in the eye. Now, we can make the assumption that after this, if the green light comes on, animal's going to blink. But what about the red light? The red light has never been associated with getting a puff of air in the eye. It's never been associated with blinking. It's only been in temporal contiguity with the green light. And if there was a connection formed, way back here, then we would expect if we showed the red light, basically the animal says stimulus association. When I see the red light, I think of the green light, and the green light makes me blink. So the red light's going to make me blink. So this is the procedure. Remember how letters can just represent stimuli? Here, RG, red light, green light, and no reinforcement. This is the first stage. We do this many trials. We got to be careful though. We have to be careful because of habituation. If we do this too much, the animals habituate to both stimuli and they don't attend to them anymore. So we can't do this a lot. We have to take into account habituation. Then we reinforce the green light. Green puff of air, green puff of air, green puff of air. Then we test the red. And if the animal responds to the red light by blinking, the only way it could have done that is if it made an SS association here. Why? Because there's nothing else that it could do. There's no responses here. There's no SR associations. The red light has never been associated with blinking, never been connected with the behavior or response of blinking. It's only been connected with another stimulus. If it blinks to the red light, we know that during the first stage, the animal made an SS association. Okay, let's look at another experiment. This experiment kind of provides some evidence for both SS and SR, and it all depends on how you interpret it. And the results first. This is known as US devaluation experiment. Sometimes it's known as revaluation. Sometimes it's US revaluation experiment. But this one specifically is called a devaluation. So I pair a light with food, with a dog. I do a Pavlovian experiment, maybe. I do this over and over. Light, food, light, food, light, food, light, food. And what does the animal do when it sees the light? It salivates, right? We've gone over. That's the first stage. I create an excitatory appetitive association. Second stage, I revalue the US. I give that animal that food that I used in the experiment, and then I hit him with some lithium chloride. Sorry, that's a really big needle. And then he gets very sick. Okay, that's a little disgusting. But I make so that the food does not make the animal salivate anymore. If I show that animal food and it smells it, it's not going to eat it. That food makes them sick, right? This food used to make them salivate, but then I devalue it. And now it doesn't anymore. So it doesn't produce the salivation anymore. The animal's not salivating because it's not thinking about eating this food because that food makes him sick. And then the question is, what does it do to the light? So let's think back to this. If the animal, after this association, now the animal hates the food, sick by the food, and then we just show them the light. If the animal made a stimulus association here, SS. When I see the light, I think of this food. When I see the light, I think of this food. What should it do? Should it still salivate? No. The light equals that food. The light tells them that food's coming. I don't salivate to that food anymore. so I'm not going to salivate to the light. And maybe at the end of this first stage, it's salivating 10 drops of saliva, and then after we test it, it's not salivating at all. The light signals food. I don't like that food. I don't salivate. But what if during this phase, the animal is making some association between the light and just salivating? Just salivating. So we're back to this again. The light and the food become associated, and now the food is no good. So if the animal thinks of the light and then it connects to the food doesn't make him salivate. The animal shouldn't salivate when the light comes on. But if it's making a connection just between the light and the response, it doesn't matter if we revalue this. We have a connection, a direct connection, SR. What's happening here? If the animal salivates to this light, then it must have made a stimulus-response association. Because if it made a stimulus-stimulus association, it wouldn't salivate. Because that light tells the animal that that food's coming and he doesn't want that food. But maybe it's just a light to response. Now, if the animal doesn't salivate at all, then it made a light to food association. Here are the possible results. So before we revalued or devalued the food, when the light was just associated with this delicious food, the animal salivates to the light 10 drops. Now, after, when the stimulus is associated with food that the animal doesn't like, bad food, and there's an SS, we would expect a drop in conditioning here, because this drop says that it doesn't like that food as much as it did before. In other words, give the animal light and food, it loves the food, it eats the food, the light produces a big salivation response. Then we devalue the food, and we wonder if the animal made an association between the light and the food, and it doesn't really like the food very much, we would get a drop in a response. Salivated 10 times, now it's only salivating 5. That drop supports the idea of SS associations. The drop itself tells them that light tells me that food's coming and I don't really like that food very much, so I'm not going to salivate as much. However, if it absolutely only made a stimulus-stimulus association, that light equals food, and I will not salivate to that food at all. SS, light, food. Then it should have been all the way down to hardly anything at all. But the fact that we could get responses, a little bit of response, compared to maybe a control group that never had this experience, the fact that we get a little bit, an elevated compared to a control group, shows us that there was some associations made between just light and I salivate. Light, salivate. That's what I do. Light, stimulus, response, salivate. Okay? So the drop in response gives us an indication that the animal made an association between the light and food and doesn't like that food very much anymore. But the fact that it still shows any response compared to a control group, any response at all, makes us say, well, the stimulus tells them that food's coming, doesn't like the food, but that stimulus also just tells them to salivate. SR, response, light, salivation, direct, in the brain, SR. That's getting a little bit complicated trying to interpret these results. So you might need to go over this a few times.